AP Review Lesson 8. In this lesson we'll take a look at some free response questions regarding equilibrium. So we're actually going to just do one big question with a bunch of parts. Now these types of questions are very common in the AP exam. Historically, the very first question on the free response portion was over this idea of equilibrium. It had the student do a bunch of calculations regarding equilibrium. Here we're going to take an equilibrium problem that involves what's called KSP. KSP, remember, is something called solubility product. And solubility product is essentially applying the equilibrium idea to insoluble salts. In fact, AgBr here is an insoluble salt. AgBr is a solid because bromine is one of the robbers to silver, or I'm sorry, silver is one of the robbers to the halogens, which includes bromine. So silver bromide is not soluble in water. However, a tiny amount of it is soluble. The tiny amount usually is insignificant, but for chemical systems it can become significant. So we express it using a KSP, an equilibrium value. Notice how tiny it is. Notice that it is 5.0 times 10 to the negative 13, really tiny, which means that at equilibrium, our products over reactants, our products is really small, and our reactants is really big. That's how you get this tiny number, which means most of our reaction still is on the reactant side. And that makes sense because K is an indication of where the reaction lies, whether on the reactants or on the products. So usually for the first question they simply ask you to write the expression for the solubility product. Now because the idea here is that silver bromide is trying to get dissolved. So silver bromide, if it were to dissolve, dissociates into Ag plus and Br minus. And essentially, if you remember, solids don't go into the equilibrium expression, but aqueous solutions do. And it's aqueous because we're showing the solubility of the substance. We have the solubility product. So our KSP is actually just the two products, because solids do not go into the equilibrium expression. So we essentially have Ag plus times Br minus. And that's why they call it the solubility product, because it's the product of the species that are soluble in water. And that's really all they want here. And now they want us to calculate the value of Ag plus in 50 milliliters of a saturated solution of AgBr. So for this purpose we're going to use the icebox. Let's go ahead and set up our equation. AgBr dissociates into Ag plus and Br minus. Recall the icebox keeps track of the concentrations as we get to equilibrium. Now because AgBr is a solid, we actually don't really care how much we have of it because it won't show up in the equilibrium expression. But let's go ahead and put some value in for it. So it doesn't really matter. Let's go ahead and put 10 in for the beginning. It doesn't really matter because the solids do not go into it. Initially we'll have 0 of our products, and as we get to equilibrium we'll have to lose on the reactant side and we have to gain on the product side. And remember, these x's have to coincide with our molar ratios, and we lose 1 and we gain 1 and we gain 1. That's why in all cases it's minus x plus x plus x. If this number here were a 2, then we'd have to put minus 2x, or if one of these was a 3, we'd have to put plus 3x. So be mindful of that. And then the equilibrium, we simply combine our initial and our change. So 10 minus x here, and x here. Now because this is a solid again, we don't really care for the AgBr. And our KSP is going to simply be x times x. It's products over reactants. We don't have anything on the reactants, so we can ignore that or we can put it over 1. So essentially it's going to be x squared. Now KSP is given to us as 5.0 times 10 to the negative 13, so we can say 5.0 times 10 to the negative 13 equals x squared. And what they're asking us to solve for essentially is the concentration at equilibrium. In a saturated solution means that since we threw this thing in the beaker, we threw this salt in the beaker, and essentially the salt dissolved. We waited until the whole solution became saturated, in other words, until no more can dissolve. So we're essentially asking for the concentration at equilibrium, and that's where we set up the icebox. Be ready to set up an icebox if given this type of problem in the free response section. So that's what we're doing. We're essentially asking to solve for how much we have of our product at equilibrium, and that's why we set it up this way. So it's as simple as square rooting to get x, and if you go and square root this number, you should get your x to be 7.07 times 10 to the negative 7. A lot of 7's in there. That would be the molarity. Notice that that's what they asked for, Ag+, and that's exactly the molarity. Now, sometimes they'll ask for how much of the salt will dissolve, and that will also be the answer. This is also how much AgBr dissolves. Even though AgBr is not soluble, notice a tiny amount of it, really 700 billionths, you can say, or 0.7 millionths of a mole. A really tiny amount of AgBr dissolves, but we can talk about it in terms of equilibrium, and that's the idea. Okay, we have another question regarding the same system. A 50 milliliter sample of water, of distilled water, is added to the solution described in part B, what we just did, which is in the beaker with some solid AgBr at the bottom, since we had a saturated solution. The solution is stirred, and equilibrium then is re-established. Some solid AgBr remains in the beaker. Is the value of the silver ion concentration greater than, less than, or equal to what you calculated in part B? So here's what we've got. We've got our beaker with some AgBr at the bottom, and it's saturated. It reached equilibrium. Now we're going to put 50 milliliters of water in this beaker. As we put that water in, the beaker now, we'll say, is up to here. And the question is, what will happen? Well, it turns out more of the AgBr can now dissolve. So the solubility of AgBr, or not the solubility, but how much AgBr, a little bit of the solid disappears and it essentially goes into solution. However, the molarity will actually be the same. It'll be equal because we added more water, but now more AgBr dissolved. And how much more? Exactly the amount to give us the concentration at equilibrium, which remember was 7.07 times 10 to the negative 7 molarity. So this is the concentration, this is the molarity at equilibrium. It doesn't matter how many liters you have in there, that's the molarity. The more liters you have, the more moles will dissolve, but the molarity stays the same. So in fact, the concentration, more Ag dissolves because there's more volume now, but the molarity remains the same. And this idea is just like saying K does not change. Since K is still a constant, the amount stays the same, and that's the idea. And part D says, calculate the minimum volume of distilled water in liters necessary to completely dissolve a 5-gram sample of AgBr. Now, 5 grams is pretty significant. You can definitely see 5 grams. You can weigh it on the balance. And they're asking, well, how many liters will it take? Now, we should right away say, well, quite a bit, a lot of water will be needed to dissolve this, because the amount that gets dissolved per liter, remember molarity is moles per liter, is only 7.07 times 10 to the negative 7. So imagine how many liters we need to dissolve 5 grams. Well, let's first find out how much 5 grams is, how many moles 5 grams is. So we can do 5.0 grams divided by the molar mass. Essentially what we're doing is we're doing some stoichiometry, where we put the molar mass is given to us as 188 grams in a mole. And so when we divide these two numbers, go ahead and divide these two in your calculator and see what you get. So we have 5.0 divided by 188. We should get ourselves 0.02 0.66 moles. And this is how many moles 5 grams of AgBr is. So what we have to find out is how many liters is necessary to dissolve this much. There's a number of ways of doing this, but let's go ahead and use our molarity equation. Molarity is moles over liter. Our molarity is here. This is the molarity that's soluble. So why don't we rearrange the equation to solve for liters, which would mean moles over molarity. Our moles is 0.0266. Our molarity is 7.07 times 10 to the negative 7th. So go ahead and divide these two numbers, and you'll see that the number is going to be quite big. Go ahead and do this in your calculator. And you should find yourself 37,600 liters, which is quite a bit, but we predicted as such it would happen because we have a very, very small solubility. So here we're applying the idea of solubility to the KSP. Okay, let's go ahead and finish up with this, and I think I had one more question that disappeared, so we'll take that though. There's actually two more questions I see. A student mixes 10 milliliters of 1.5 times 10 to the negative 4th molar silver nitrate with 2 milliliters of 5.0 times 10 to the negative 4th molar sodium bromide and stirs the resulting mixture. What will the student observe? Justify your answer with calculations. So this idea is solubility. This is combining solubility again with K. So remember when we did this with solubility and precipitation, we found out how many moles we have. And to get moles, remember you would multiply liters times molarity. So we got liters times molarity. In this case, our liters is 0.010. Our molarity is 1.5 times 10 to the negative 4th. So effectively, we move the decimal place over twice to the left. We get 1.5 times 10 to the negative 6th. Here's how many moles we have of our silver nitrate. Now when silver nitrate hits sodium bromide, essentially you get yourself the silver bromide solid that we just discussed. And the question is the concentration small enough to where it'll dissolve, or is it big enough to where it'll precipitate? Let's do the same thing here. Let's find out how many moles we have. Again, our moles here is molarity times liters. So our liters in this case is 0.002, and our molarity is 5.0 times 10 to the negative 4th. So you move the decimal place over twice to the left, and you would double it. So you got yourself here 1.0 times 10 to the negative 6th. Or 3 times to the left. 1, 2, 3. And you can just plug this in. Remember, you can use your calculator on this portion of the AP exam. So we have 1.0 times 10 to the negative 6 and 1.5 times 10 to the negative 6. Now recall that our molarity was 7.07 times 10 to the negative 7th, which is smaller than what we have here. Or is it? So we have this many moles of each. Now when we throw these into solution, essentially we have to divide it by the liters. So to find out the molarity of each, let's go ahead and divide by total liters. In this case it'll be 12 milliliters total. So let's divide this by 0.012 liters. Let's do the same thing here. Oops, 0.012 liters. Now when we divide by a tiny number, we'll end up with a big number. So we should expect our numbers to be quite high, relatively. So 1.5 times 10 to the negative 6th divided by 0.012. Here we get 0.000125 molar. And in the second case we have a similar 1.0 times 10 to the negative 6th divided by 0.012. Here we have 8.3 times 10 to the negative 5th molar. Now both of these, this one is actually, if we put it in scientific notation, should be 1.25 times 10 to the negative 4th. So we have 1, 2, 3, 4. So notice that both of these molarities are quite a bit higher than the solubility molarity. And because they're higher, you will form a precipitate. form a precip because the resulting molarity is higher than the KSP allowed. And that's kind of the idea. And then you'd have to show these calculations. You have to show that, notice this molarity is higher than your allowed molarity, and so is this. So we actually will form a precipitate. Now, after we precipitate, there'll be a little bit left over. And the amount that's left over can be calculated, even though they don't ask you here. You can calculate it by subtracting our two numbers. We'll actually end up with 0.5 times 10 to the negative 6th, and you can divide that by 0.012 liters, and you can find out how much is left over. And that's essentially, they don't ask this, but that would be the amount left over of silver nitrate, because it is the silver nitrate then that is excess in this case. Okay, let's go ahead and finish up with these two problems. And this is more of a qualitative discussion, but we have the color of another salt of silver. Silver iodide is yellow. Many iodide compounds are yellow. A student adds a solution of sodium iodide to a test tube containing a small amount of solid cream-colored silver bromide, what we've been dealing with. After stirring the contents of the test tube, the student observes that the solid in the test tube changes color from cream to yellow. The reason it changes color is because AgBr gets swapped or becomes AgI. In other words, the iodine replaces the bromine. So actually that's what they want us to do, write the chemical equation for the reaction that occurred. So we have silver bromide, which is a solid. We add to that iodide, ion, which is aqueous. And it's aqueous because it came from sodium iodide. All sodium salts are soluble. And so the iodine will replace the silver, or I'm sorry, the bromine, not the silver. So we'll end up with silver iodide, which is a solid, and then bromine will go into the solution, which can be aqueous. And this, by the way, is the net ionic equation for what happens. We'll review net ionic equations once more in a separate session, but this would be your answer. And here it asks which salt has a greater value of KSP, silver bromide or silver iodide. Well, because silver iodide became a solid, silver iodide is less soluble, so AgI is less soluble than AgBr. And that's because AgBr went into solution, which means it's more soluble. So what will happen then, AgI's KSP must be smaller than AgBr's. So AgI KSP is smaller, which means the KSP of AgBr is higher. Now AgBr's KSP was already tiny. Remember, it was something times 10 to the negative 14, I think. But you know, you can have a KSP that's even smaller. So a variety of questions that they can ask with equilibrium. For the homework, for the rest of the homework, I'm going to cycle through the answers real quick, and you'll see that you'll have a similar questions for our quiz in class. I'm actually going to give you a hint ahead of time. I will be asking you a question like this, a solubility question. It won't be exactly this one, but it will be the solubility of some sort of ionic substance. This completes the lesson. Let me go ahead and cycle through the rest of the questions if you didn't get a chance to get them from Edmodo. Pause as needed. Here's some homework practice. This one. Number 8. Number 9. 10. 11. Some graphs for you in 12. Some more graphs. What is this about? Looks like it's supposed to be something else. And a few more parts. And a few more parts. And D. And this is the rest of it. So this should conclude for us lesson 8.